right, so what we're getting into in this last unit is nuclear chemistry. And we're going to take kind of a bird's eye view of nuclear chemistry. Kind of hit the highlights, the stuff that we need to talk about. There's a lot more in here, actually, than we'll even begin to scratch the surface of. But we're giving you just kind of an idea of what it is, what information is important and relevant to us, and hopefully some things that we can kind of take away and apply. So let's start off with some definitions. Nuclear chemistry, first of all, is the study of reactions that involve changes in nuclei. So unlike the chemical reactions that we've talked about all semester long, since the beginning of January, these are focusing on not what happens when this atom and this atom interact with each other, but rather what happens to this atom if it happens to be radioactive. And what is radioactivity? Well, radioactivity is the spontaneous breakdown of a nucleus caused by the lack of stability in that nucleus. And when that lack of stability comes about, when that nucleus degrades, what we will see are a couple of things. We'll see the release of energy, usually high energy, stuff that can be, particularly damaging because of how high energy it is. And often we will see the release of particles. And those particles get ejected from that nucleus in a way to try to stabilize the nucleus. So one of the principles that we've always held in this class is that, generally speaking, chemical reactions or any kind of reaction, any kind of change happens because it is going to overall lower the energy, increase the stability of the substances that we're examining. Well, nuclear is no different. If I have this really unstable nucleus, when it decomposes, whatever comes out of that unstable nucleus is going to be more stable than the unstable nucleus was before. And that difference of energy from the unstable to the stable, that's what gets released. That's what we measure when radioactive decays occur. Now, there are 4 different modes of radioactive decay, 4 different ways that the radioactivity can manifest itself in these kinds of reactions. And which one we see ultimately depends upon the nucleus itself. We have 2 descriptions of nuclei. We can either call them neutron-rich, which is a fancy way of saying it has too many neutrons, or we can call it neutron-poor, which is another fancy way of saying it has too many protons. So the 4 types of decay are what are called alpha decay, beta decay, positron emission, and electron capture. Those are the 4 primary types of radioactive decay. And which one we see largely depends upon what is wrong with the nucleus. Is it too heavy? Is it too neutron rich, too neutron heavy? Is it too proton heavy? Now, one way that we can measure stability, or at least predict stability, is using a graph like this. This graph is called the belt of stability. The belt of stability is relatively simple. On the vertical axis, I have the number of neutrons in the nucleus. On the horizontal, I have the number of protons in that nucleus. Each one of these dots, orange and green, represent a known isotope of a particular element. Now you can see that for some of these atoms, for some of these elements, because remember, protons equal atomic number. So any of these dots that are in a vertical column would all be isotopes of a given element. So if I'm looking at element number 60 here, all of the dots that fit on this x equals 60 line, these are all element number 60, neodymium, Nb. And so you can see there are lots of different neodymium isotopes that are possible. The ones that are orange are known, but are also known to be unstable. The ones that are green are known and also stable. And what we can see, if we zoom in on this a little bit, is that for most of the elements that we encounter on a regular basis, elements 1 through 20, most of those elements follow a pretty close to 1-to-1 ratio of protons and neutrons. To help us see this, that's what the purpose of this purple line is in the graph. Represents a 1-to-1 ratio of protons and neutrons. And we can see that for these light elements, going up to about calcium, most of them fall on that line or just a little bit above it. And if we look at the molar masses of those elements, we see that. Average mass of carbon is 12. Well, carbon has 6 protons. 12 minus 6 is 6 neutrons. Phosphorus has a molar mass just about 31. Atomic number is 15. 31 minus 15 is 16. There are 16 neutrons. So, for the most part, in that first 20, we see pretty close to 1-to-1 ratios of protons and neutrons. But notice that this line begins to bend right around calcium. As soon as we get to calcium, it starts to bend up a little bit. And by the time we get way up here to our last known stable isotopes, it has been pretty considerably off of that 1-to-1 line. Now, can anybody give me a possible explanation for why a 1-to-1 ratio doesn't necessarily work once we get to bigger and bigger atoms? All right, well, let's phrase it this way then. What is the charge of a proton? Positive. What's the charge of a neutron? Nothing. If I start packing in, let's just take tin, for example, element number 50. I've got 50 protons. Those 50 protons are all positively charged. How compact do you think I can get those 50 protons to be without just having the whole thing break apart because of all the repulsion? That's the problem ultimately, right? All those protons are going to repel each other. And so it becomes a matter of spacing. In the small atoms, there aren't enough of them to really cause any problems. So a 1-to-1 ratio makes sense. But as our atoms get bigger, we're going to have more repulsion. We're going to need more neutron spacers in between to keep those protons apart from each other so that the nucleus doesn't just fly apart and break into protons and neutrons individually. So that's why we see this bending occur, because as the atoms are getting bigger, we need more of those neutrons, those neutral spacers in between those protons to keep them from getting too close to each other. So if all of those yellow dots represent some kind of radioactivity, some kind of unstable atom, an unstable isotope, what are the different ways that we can get back to stability? Well, let's take, for example, the first one here, beta decay. In beta decay, what we see is the spontaneous ejection of a beta particle. A beta particle we can think of as being very similar to an electron. And what does that mean? Well, if we look at our diagram here, we can see that these black spheres are representing neutrons. These gray spheres with the positive signs in them are representing the protons. This black sphere has converted into a gray sphere in the process. So what we see in beta decay is the conversion of a neutron to a proton inside the nucleus. Now, how does that work? Well, that's where we get into a lot more nuclear physics kinds of discussions about what subatomic particles there are. We get into quarks and muons and bosons and all that other stuff. That's way beyond the scope of this course. The way I figured the easiest way to kind of explain it is this. Let's imagine that the reason a neutron is neutral is because it has both a positive and a negative piece inside of it. And that's why it's neutral. The two are canceling each other out. Well, beta decay in this form of this negatron basically means that if I've got the positive and the negative both here at the same time, if I get rid of the negative particle, the positive's still there. And so that's how we can kind of rationalize this idea of a neutron turning into a proton. If I get rid of the negative charge that is neutralizing that neutron, what's left is going to be a positive charge. And since protons and neutrons are almost about the same weight, it kind of makes sense. Now, is that actually what happens? Not really. But it's an easier picture to kind of visualize. That's what we're going for. Alpha decay is, so let's go back to beta for just 1 second here. So what we tend to see is for the yellow dots that are on this side of the graph, these are the ones that have too many neutrons. And down here below the band of stability, these are the ones that are neutron poor. So we just saw an example in beta decay of what can happen if I have something that's neutron rich. So any of the ones that are above that band of stability, beta decay is one of the ways, the primary way, that they go about getting toward that band of stability. But what about those that are up here? If our atomic number is greater than 83, 83 being bismuth, bismuth is the last known stable isotope, element that has stable isotopes to it. After bismuth, all of the elements are radioactive and unstable in some kind of way, even if they occur naturally. So you'll notice a difference in the atomic masses of those elements. Most of them are in brackets because they only exist as radioactive particles and they're largely synthetic. For the ones that aren't that way, like thorium, protactinium, uranium, those ones naturally occur, elements 90, 91, 92. But even though they naturally occur, they're naturally radioactive as well. So even if they have multiple multiple isotopes, all of the isotopes are unstable. There are no green dots beyond element 83. So what happens if we are above element number 83? And we're not just dealing with a neutron-rich, neutron-poor kind of situation. Well, in that circumstance, that's where alpha decay comes in. Because in alpha decay, what it allows the unstable nucleus to do is basically shed weight. The alpha particle is not just a particle. It's a nucleus. It's got 2 protons and 2 neutrons. If that sounds familiar to you, that's because basically that's what helium is. The only difference between an alpha particle and helium is the electrons. Helium has 2 of them, an alpha particle doesn't. So when we look at those trans-bismuth elements, one of the most common forms of decay they undergo is alpha decay. Because in order to get to that band of stability, they've got to lose some weight. Now, when we're looking at those elements, when we're looking at those different isotopes, what we need to understand is that for a lot of them, especially the ones that are in that really radioactive range, your uraniums, your neptuniums, your plutoniums, they're going to go through a series of decays to get down to something stable. It's not going to be just a simple alpha decay and now I'm good. When we see multiple nuclear decays happening for a given isotope, we call that a decay series. And so here is one such series for the isotope uranium-238. So uranium-238 is an unstable isotope of uranium. If it undergoes its natural processes of radioactive decay, it is first going to go through an alpha decay, then it'll go through a series of beta decays, then it'll go through a series of alpha decays, and then depending upon circumstances, it might go through some beta decay, it might go through some more alpha decays, until eventually it gets all the way down here to lead-206. And lead-206 is a stable isotope of lead. But if you follow the arrows here, you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, somewhere around 15 decays took place to go from the unstable uranium to the stable lead. And the thing about these radioactive decays is not all of them are fast. Some of them can take quite a long time to develop. And so if you're looking at why is there such hubbub about nuclear weapons, nuclear power plants, those kinds of things, well, we're talking about uranium in most of those cases. And in most of those cases, even if we have the reactions take place, the resulting products that are radioactive can take years upon years upon years upon years to get to anything stable. And why is that a problem? Well, because all of these decays are going to release radioactive particles. That radioactive particle is going to have energy associated with it, and that radiation can do damage to whatever's around it. So there becomes a matter of what happens after. We use it for nuclear power. What happens after the power plant? How do we get the stuff safely to a site, safely to a place where that radiation that's coming off of it isn't going to hurt anybody? Always going to be the question that we have to ask. All right, positrons. Here's our third form of decay. Positron emission is kind of the reverse of beta decay. In that, we have a proton that is turning into a neutron. And so, again, this happens in neutron-poor nuclei, so we're looking at things that are below that band of stability. So, example of this, carbon-11. Carbon-11 is an unstable nucleus of carbon. When it undergoes positron emission, it will turn into boron-11. Boron-11 is the most common stable isotope of boron. Now, again, from a rational kind of thought process in terms of what's going on inside of that nucleus, well, again, if you think about that proton's got an extra positive charge. It gives away that extra positive charge. What's left over is neutral. That's where we can get the neutron out of that. So we don't want to go too deep into this idea of antimatter because, again, you can get very deep into the weeds of nuclear physics very, very quickly. But one thing we have to understand is that there are opposite particles to every subatomic particle that we know. So for electrons, there are positrons. For protons, there are antiprotons. Now, we don't talk a whole lot about antiprotons because for the most part, they never really come into our consciousness. But one thing that we do know is that when those two antiparticles come into contact with each other, they go through what is called an annihilation. That annihilation process basically turns whatever mass that they have into pure energy. So in the case of a positron and a negatron, a positron and a beta particle. Those two things, if they come together, they go through an annihilation reaction. The result is a whole bunch of energy being released. We call that energy gamma rays. And so gamma rays represent the most high energy form of radioactive decay. This is the energy that is the most dangerous, it's the most ionizing, it is the most powerful of all the kinds of energy that are associated with radioactivity. And this is how it gets its origin, through these annihilation reactions. All right, last form of decay, electron capture. Electron capture looks very similar to positron emission. And we can see that because we're again dealing with neutron poor substances. The only difference is that instead of a particle being ejected by the nucleus, the proton giving away a positive charge, what we see instead is that this unstable nucleus grabs one of the core electrons, one of those inner energy level electrons, and in that process turns that proton into a neutron. The reason we have both of them is because we have experimental evidence for both, where we can see the release of energy from this electron capture, from the increase of stability, that extra energy goes out, but we see it without the particle coming out as well. So we can detect positrons when they come out. And we notice that there are reactions that look like positron emission, but don't actually have positrons. And so electron capture is the way that we have rationalized this kind of observation. So if we look at all these kind of together, some of this information here is essentially the same as what we've seen before. Here we have a neutron. Here's its atomic mass. Here we have the proton. Here's its mass. We can see that the two masses are very, very similar. They only differ on the fourth significant figure and beyond. Notice also that the electron and the positron, they truly are antiparticles of each other. Same mass, different charges. So literally, they are the same thing, just with a positive or negative charge. They are antimatter particles to each other. This last bit with deuterons and alpha particles, a deuteron would be a hydrogen nucleus that has a proton in it. You may or may not know deuterium. Deuterium is the form of hydrogen where instead of just having the proton, we have a proton and a neutron in it. There are three known isotopes of hydrogen. Hydrogen, the one that we're most familiar with, deuterium, deutero, meaning two particles, the second particle being a neutron, and tritium, the third particle also being a neutron there. So deuterons have this mass here. You'll notice that basically a deuteron is half of an alpha particle, which again should make some sense, because an alpha particle is a helium nucleus instead of just a double dose of hydrogen. We're actually going to skip this because we got a couple of extra minutes. Let's talk a little bit about how we monitor and track these kinds of reactions. So this is getting into that assignment that is due. That assignment 21.1 is all about these kinds of reactions. Now, unlike chemical reactions, which we are very focused on how many atoms of carbon do I have? How many atoms of hydrogen do I have? How many atoms of oxygen do I have? In nuclear reactions, we're not going to be worried about conserving mass or conserving atoms. We're going to be worried about conserving particles. And so the way that we track the particles is through looking at two things: total mass number, so that is the total number of protons and neutrons, and total charge. We're going to track total charge using atomic number. Those are the things that we need to track. So the way that we know that a nuclear equation is balanced is we look at both sides of the equation and we say, okay, what are the atomic numbers on the reactant side? What are the atomic numbers on the product side? Do they match? If I add up all of the reactant, I add up all the product, do the numbers match? Do the numbers match for the mass number? If I look at the mass numbers of the reactants and the mass numbers of the products, do they match up? If the answer to both of those questions is yes, then we have a balanced nuclear equation. If not, then we need to do some more work, or we need to rethink what it is that we are looking at. So most of the time, balancing nuclear equations isn't a matter of coefficients. It's a matter of kind of figuring out what the missing piece is. So let's take a look at a couple of examples. Here, polonium-218 undergoes both an alpha and a beta decay. What are the nuclear equations for this? So we need to start with polonium-218. Polonium-218, polonium is element number 84. So if you have forgotten, because it's been a while since we were in chapter 2, this form of notation gives us the mass number, which is the number of protons plus the number of neutrons, the atomic number, which is just the number of protons, and the element symbol, all in that one package. Now, if there is a charge, which usually in nuclear reactions, we aren't concerned with charges as much, but if there was, it would be here on the upper right-hand side as well. Again, nuclear reactions, we're not usually concerned with charge because everything's got a funky charge anyway. We're really concerned about the nucleus, and electrons aren't part of that nucleus. So if we're undergoing alpha decay, The alpha particle we can write as either 4,2 alpha or 4,2 helium, since the atomic number 2 corresponds to the element helium. We can go either way. For the purposes of sticking with the nuclear notation, I'm going to use the alpha here. But again, understand, you could put helium in that spot, it would be just fine. So the question here really is, what's the product after this polonium goes through its alpha decay? Well, to answer that question, we need to go into those conservation ideas. The total mass number of polonium was 218. That means that the total mass number on this side of the equation also has to be 218. So if the alpha particle accounts for 4 of that, the other particle, whatever it is going to account for the rest. 218 minus 4 would give us 214 as the mass number of whatever it is that we are looking at. Now we go to the bottom of the equation. Bottom of the equation says that there are 84 protons in polonium. Well, the alpha particle accounts for 2 of those. The others have to come from somewhere else. Where do they come from? Well, 84 minus 2 would give me 82 as the atomic number. I look over at the periodic table. I see element number 82 is lead, Pb. That's it. That's all we have to do. So that's the alpha decay. Let's look at the beta decay. In the beta decay, we're still talking about polonium-218. But this time it's undergoing beta decay instead of alpha decay. Now, a beta particle has no mass and a -1 charge. Because after all, a beta particle is an electron. Electrons, relative to protons, have no mass, and they have an opposite charge of the proton, so that's where the -1 comes from. To figure out the missing particle here, I've got to go through the same process. There are 218 as the mass number of polonium. The beta particle accounts for 0 of it. So all 218 must be in our daughter nucleus, the result of this radioactive decay. As far as its atomic number is concerned, 84 was the atomic number of polonium. Right now we have an atomic number of -1. 84 minus -1 would give us an atomic number of 85 for this nucleus. Element number 85 is At, astatine. And so that would be the product of the beta decay of this polonium isotope. All right, so we'll do a little bit more with that on Friday as we start to kind of gear into looking at other ways to view nuclear chemistry.